So now let's look at the uniform convergence of the power series. We let A be a subset of the domain of convergence of the power series C sub k times x to the k. So we define a function f, okay, which is function f of x, which is equal to this power series on this subset A. And we also define the partial sum, right? The partial sum S sub n of x, which is the summation k from 0 to n on the same set A. So then this S sub n of x forms a sequence of functions, right? So it's a function. First, for the different x, you have the different values. So it's a function. So it's a sequence of functions. And if we say the sequence of functions converges uniformly to function f, okay, so you can review the definition for the convergence of the uniform convergence of the sequence of functions. If the sequence of function converges uniformly to the function f, then we say this power series converges uniformly on the set A. Okay, so now let's look at a lemma. The lemma says if there exists some constant n and some constant alpha is from greater than or equal to 0, less than 1, such that c sub k times x to the k's power is less than or equal to the absolute value, is less than or equal to the some constant m times alpha to the k for all k and all x in the A. A is a subset, as we discussed previously. A is a subset of the domain of convergence. Then this power series converges uniformly. Okay, so we want to prove this result. So by the definition, if the power series converges uniformly, we just needed to prove that this sequence of functions converges uniformly. Okay, so if this sequence of function is given by this form, this is a finite sum, and so now we want to prove this sequence of functions converges uniformly. So we want to use the idea, which is the Weierstrass convergence, uniform convergence criteria. Okay, so we want to prove that this sequence of functions is Cauchy, uniformly Cauchy. Okay, so let's look at the proof. So we let s sub n equals c sub I times x sub I from 0 to n. Okay, this is the partial sum. Okay, so let's take the difference of this is by the definition of the uniform Cauchy. Okay, s sub n plus k minus x s sub n. Okay, which is equal to c sub n plus 1 times x to the n plus 1 plus c sub n plus 2 x to the n plus 2 and plus and so on, plus the last term, which is c sub n plus k times x to the n plus k. Then we use the triangular inequalities. It's less than the absolute value for each term, right? We add together. And we know each term is, this is the condition, is bounded by m times alpha to the k's power, right? So here k is n plus 1 for the first term. The last term is n plus, the power is n plus k. Okay. Then we can use the geometric sum. Okay, geometric sum. This is given by this one. Okay. Then we use 0 to replace this number alpha to the k, alpha is less than 1, greater than or equal to 0. So it's less than or equal to, right? Less than or equal to this one. Okay, so this one, so there is nothing about k anymore, right? If we take n approaches infinity, this would be alpha is less than 1, so this would approach 0. So this, the whole term will approach 0. So we see this sequence of functions s sub n is uniformly Cauchy. Okay, then we apply the Weierstrass uniform convergence criterion, and this sequence of functions is convergent uniformly. Okay, so by the definition again, so the power series converges uniformly on this subset A.